My name is Jamin Park. I'm a postdoc here working with Javier and Navier. I'm going to be in charge of the next lectures. And actually, it's my first time teaching in Spain, so I don't know how it goes, but I will just try my best. So the main theme of the next lectures can be summarized as follows. So mainly, we will be interested in the stationary solutions to the Euler equation. So on the one hand, we're going to prove that for the positive or non-negative vorticity stationary solutions. So we are going to prove that the omega has to be radially symmetric. Yes. Yeah, sure. I mean, I'll describe just two main objects, and then I will go over some details later on. So, symmetric. And the second part is going to be by allowing this, by allowing the omega to change sign. Okay, so for omega, sign changing. We are going to construct a non-radial stationary solutions. So this is the main object that we are going to study. Of course, there are some variations. We will also consider not just only stationary solutions, but we will consider some rotating solutions as well. Yes, but like for the details, I will point out when the time comes. Okay. So the camera, I can start from here.
No, it's in the red.
The red here, this one?
No, the second.
The second?
Yeah, you can follow the other.
Okay, so I can write from here to here.
Yeah, that's the same camera. Same
Okay.
camera, so okay, now the second one.
Okay, see. Thank you. Okay, so as far as I know, Javi and Claudia, they go over some like basic concepts about the incompressible flow, but I will just make some concepts more clear. So let's recall the Euler equation. So we write the equation in the vorticity form. So the equation reads as omega t plus the vector field u times the omega equals to 0. So we have a transport equation. The omega is a scalar value function. And we consider this equation in the following domain. So our spatial variable lives in the whole plane. There's no boundary. And what's the vector field u? So u is given by the grad curve times the inverse Laplacian of omega. And then, because this is an evolution equation, we consider the initial value. Then what do we know about this inverse Laplacian? So here, the spatial domain is R2, so we can write the inverse Laplacian can be written as a convolution with the Newtonian potential, where this Newtonian potential is a radial function that is given by 1 over 2 pi times the magnitude of x. Okay? And then I'm going to use the notation psi to indicate this the convolution term. So the vector field is just the gradient curve of psi. So just in case we recall that here, I think I should have mentioned the gradient curve means the gradient is a vector, right? So we take a rotation and the right angle counterclockwise, which is negative. So this gradient curve means we take the gradient, which gives you a vector, and then we rotate 90 degrees counterclockwise. Okay. Any questions or okay, so all good. And then we are going to consider 3 types of solutions for those equations. Before that, I'm gonna use another. Okay, so 3 types of solutions. So maybe there are more different kinds of solutions for this equation, but basically we will be only interested in these 3 types of solutions. The first one is what is called a vertex patch. So imagine your initial data is a characteristic function defined on a certain domain D. Of course, we consider D is a bounded domain R2. So in the plane, if you have a domain here, say D, and then because this equation is transport equation, the solution at time t, it stays as a characteristic function, but what changes is just the shape of the domain. So we can write it as still a characteristic function, but the domain depends on time. So what I'm saying is, okay, so if we have a characteristic function defined on this domain, then it gives you a velocity vector with this relation. Say we are going to have some velocity vector like this. I don't know if this is incompressible, but then along this vector field, the shape, the figure of the domain will change. So, like for example, in this case, it will be stretched in this direction, and it will be stretched in this direction as well. So in time, your domain changes, but it still stays as a characteristic function. And then the second type of solution is just classical solution. smooth. So we just consider the solutions as smooth as you want. By this notation, what I mean is the solution that is smooth in time and smooth in spatial variable as well. So nothing much to say about this. Just you have a smooth solution that solves the equation in the classical way. But we also consider complex efforts. So like, I'm assuming the nicest situation that one can have. So there's no any like pathological behavior of the solution. And the third type solution is what is called the vertex sheet. I'm not going to talk about this type of solution right now, but when we get to this point, I will explain more details. But this is a weak solution. But it's a measure, I should say, measure value. It's a measure value weak solution concentrated on curves. So it's very weak. It's not even like even a function. Just measure value solution. I will not talk about much at this point, but I will explain more details as the time comes. Any questions at this point? I think that most of the material was already covered in the previous lectures. Then, as I mentioned in the beginning, we are interested in the stationary solutions. So let's consider stationary solutions. What do I mean by stationary solutions? So, stationary solutions means a solution that doesn't depend on time. So at each time, the solution is just the same as the initial value. So as time goes on, nothing really changes. It's very easy. And then as a variation, one can consider a rotating solution. So for the rotating solution literally means, so you're given a initial data, and then we run this equation. So as time goes on, your solution changes, but the solution just rotates. Its behavior is very simple. More precisely, we consider the rotation matrix. How should I? Theta will be, it's a matrix, just 2 by 2, like the cosine theta. Now I'm confused. Is this something like? No. Is it maybe negative sign theta or something?
Just in the other direction. It doesn't matter.
Doesn't matter. And then like I think this should be a sine theta, and then a cosine theta like this. Does anyone know?
So it's positive direction.
Positive direction. Oh, sorry. So can you say that again?
It's positive direction. It's left.
So this matrix is right. So this matrix, this rotates the vector in the positive direction, right? By theta. So basically, if you're given a vector, say v, then the r theta times v is going to be rotated by angle theta in this way. Then your solution and t is just rotating with the constant angular velocity, the rotational time. So that will give you that will be given as the rotation of the initial data, which will be negative omega t times x. Something like this. So at each time, you just rotate the initial data. But that means just the solution is rotating with time. But here we consider the omega is time independent. So we call it uniformly rotating solution. So rotational speed doesn't really depend on time. And then maybe most of the concepts are just one thing. So let's consider this vortex patch problem, and let's suppose we have a rotating vortex patch, and then see what conditions can be satisfied for such solutions. We have that if a vortex patch is rotating. Whenever I say, like in this class, whenever I say the solution is rotating, I always mean that the rotation is uniform. So always I'm going to assume that this angular velocity doesn't depend on time. So if this vortex patch is rotating, then what one can see is that the string function minus this one is constant on the boundary of V. Okay. I think Claudia already mentioned this condition before. So should I go over why, or can I just skip this part? Or yes. Does anyone have any? Okay, so let me just quickly go over like how we can have this condition. We can just ignore. I'm going to just ignore this angular part. Just I'm going to consider the stationary solution, for example. So what do we know about the Euler equation? So Euler equation tells us that if we have a string function like this, then the velocity vector is given as a grad curve. Then what does it look like? So let's imagine the level sets of the string function. And then we know that the gradient is just a vector that is perpendicular to the level set. So gradient is going to be something like this, right? And then we take the perpendicular, we take the rotation. So the velocity vector is always like tangent to the level set of the string function. Right. So in this case, if we ignore this part, this means that the psi, the string function, is constant on the boundary. That means the boundary of the patch is the level set of the stream function, that means that the velocity vector is always tangent to the boundary. That means the velocity vector, the flow doesn't change the shape of the domain. So if the domain doesn't change the shape in time, then the solution is stationary. Because each like fluid particle is moving along the boundary. There's no like normal velocity components. Okay. And then when we add this omega, when we consider like rotating solutions instead of stationary, then we can consider this argument. We can just make the same argument in the rotating frame. So instead of saying that the solution is rotating, we consider the frame is rotating in which the solution is stationary, and then just make the same argument. Okay. But let me make it more precisely. I'm going to write it as a definition. Let's D, which is a boundary subset in R2, be so for a boundary subset in R2D, let's suppose omega is a rotating solution. Oh, this is not a definition. So we say, we say that a patch solution is a rotating solution with the angular velocity omega if the stream function minus this guy, which is defined as the convolution with the Newtonian potential minus this quantity. If this is constant on each connected components of the boundary D. Okay. So here, so what's different between like this like more like rigorous definition and that concept that I just earlier mentioned is that so there I was implicitly assuming that the patch is just simply connected, but if you consider like non-simply connected patches, then you may have some disconnected boundaries. For example, imagine your domain has a hole here, okay? Then you have like two disconnected components. The one component is the outer boundary, and the other one could be the inner one. Or if you want, you can add like one more hole. Then we have like three connected components of the boundary. So what we require for a solution to be rotating is that this one, the stream function minus some quantity, is constant on each of them. It has to be constant on the outer boundary and two inner boundaries. But here we do not require those constants to be the same. So this one may have some different values on each boundary, but they can have like, they are allowed to have different values. So, have different constant values on each. Because as we saw here, all we need is that the boundary is a level set of this guy. Right? Any? Yes.
So do you get any restriction with the relation of the constants or
The relation of the constants?
your model of component?
Yes.
Is it possible that this constant is
Different?
any number, or do you get some like restriction for that?
It could be any number. Yes, yes. Wait. Let me. So you're asking if I'm given like two any numbers, then if I can construct a rotating solutions for which this guy has those given numbers on the boundary. Yeah, maybe certainly. I mean, for two numbers, maybe you can do it because, like, I think Claudia already mentioned, but any regular functions are rotating solutions, right? So okay, so imagine you are given like two constants, for example, then you just consider an annulus, and let's suppose so this is so omega is 1 here, well, omega is 0 here, and omega is 0 in the outside. And let's consider this, the radius of the smaller circle is b, and let's fix this guy as a 1, something like that. Then one can like just modulate this b so that this guy obtains some constant, like the given constant on the inner boundary and the outer boundary as well. Technically speaking, yeah, something like that. It's not really like a rigorous argument, but you can certainly make you can choose B so that but you understand what I'm saying. Okay. So let me skip part. Maybe you can discuss after the lecture. But actually, to understand the structure of the solution, the specific values don't really matter. You will see why. Because like when we say the solution is rotating, actually what we need, we don't really need the information of its side, but we need the information of the gradient of the side, because the gradient of the side is the velocity. So like the specific number, the constant doesn't really matter, but what we really need is its variation, its gradient. Say like the difference between two constants on each boundary, something like that. Okay. And then I will write down the theorem that I'm going to prove today. So this is the main material that I want to go over. theorem is the following. Suppose the patch is simply connected. And the characteristic function defined on such a domain is rotating with the angular velocity in the following region. Then is as far as I remember, Claudia, she gave a proof that one can actually find a simply connected vortex patch solutions that is rotating with the angular velocity, some values in this interval. But what I'm going to prove, what we are going to prove, is that there is no rotating solutions that is rotating with the there's no rotating solutions that is rotating with the angular velocity not included in this interval. Okay.
Maybe you can know that like the horizontal axis omega is the solution. And so Claudia would be the other way.
Sorry, can you say? The bifurcation diagram.
Yeah.
Okay. So let's recall that the Claudia's lecture, what she proved is that so the setting is the following. So let's consider a star-shaped solutions. Star-shaped domains where the boundary given angle theta, the boundary can be parameterized as I can't. So imagine you have a star-shaped domain. This is star-shaped, and then the boundary can be parameterized as in the casual way, like the boundary is function of theta in this way, so that each point on the boundary, and then when you look at the distance between the point and the origin, and that can be simply given as a function of r. Then we already know that if this r is constant, then this star-shaped domain corresponds to a disk, which is a rotating solution. But then the question is whether one can find a solution for which this r is not just constant, but it varies in theta, right? What you proved that so we can consider some functional space that represents this r, and then say this horizontal line corresponds to a constant function. So like if you give me a point that corresponds to a certain angular velocity and a constant function for r. But what Claudia proved that if the angular velocity lives between 0 and 1/2, And there are some bifurcations, something like this, so that each point, it corresponds to a certain angular velocity, and that point, the boundary is not just a constant, it's a function, like non-constant function that corresponds to non-radial solutions. But what we can prove is that, like, whatever curve you have, this curve cannot go beyond this vertical line, because if it goes beyond, then your angular velocity becomes larger than 1/2. That's contradicts to this result. So every non-radial solution, for every non-radial solution, its angular velocity has to be confined on this open interval. And of course, here we do not assume the star shape, so it's a little bit more general, like, and yes, so like for any, in general, like star shapes are, and in general, like for simply connected domains, there is no rotating solutions for the angular velocity less than or equal to 0 or bigger than or equal to 1. Is the statement clear at this moment? Okay. Okay. Before we get into the detailed proof, so I'm going to just write down the idea of the proof. So let me first make a remark. It's scaling invariance. So in general, if omega x doesn't have to be a patch solution, it could be just any solution. If this is a rotating solution, if this is rotating with the angular velocity omega, then omega a of ax is also rotating with the same angular velocity, where omega ax is the rescaled verticity in the spatial domain. Of course, here, like, A is a positive constant, right? So if you pick large A, then, and your domain looks like this, then for large A, your domain like shrinks, right? But still, it's a rotating solution with the same angular velocity. So the proof is very straightforward. And then now I'm going to describe the idea of the proof. So the first observation is that we can like shrink or like what's the antonym of shrink, or make large as we want, so that we can just assume that the patch, the area is just 1. That means that we can given rotating solution as a probability measure, P density. Same. And then the second point is that we will define energy functional for which the stationary patch is a critical point. Is a critical point under some suitable perturbations in the probability measure space. Of course, I'm not like specifying like what probability space I'm considering, but it will be clear when we get into the detailed proof. And then we are going to show that any critical points, let's say the functional defined here, let's call it E, is a disk. Okay, so that's the steps that we are going to follow. So if we can prove all of these three, or if we can do all of these three steps, then the result follows immediately, because imagine you're given a stationary solution. Wait. I'm sorry, you're working on the rotating solution, not stationary. Solutions. Okay. So if we are given a rotating solutions, then we will treat this rotating solution as a probability density. And then at the second step, we will prove that that is a critical point of some energy. But the third stage says that any critical point has to be a disk. That means your given rotating solution has to be a disk. So the proof is done, right? Sorry?
In which of these steps do you use that omega is not to be seen?
Yeah, actually this functional depends on omega. So I will say if omega is in this region. I'm sorry, I should have mentioned this. So if your solution is rotating with that angular velocity, then this is a critical point to a certain energy. But for this energy, if the angular velocity is contained in this region, then its critical point has to be a disk. So but the first part is easy. We have a characteristic function whose integral is just 1, right? Because we can always shrink or enlarge the domain size without changing the angular velocity. So the first part is easy. And let's see the second part. So we have to define the energy. And then it's a critical point under some perturbation. So still like this perturbation, it means something vague. So we have to clarify what perturbations we are considering. So let's get into here. So given a density, probability density are 2, 1, and 2. We define E of rho to be that depends on the angular velocity. We define E to be 1/2 of the rho times the Newtonian potential involved with rho x minus rho. That's the energy functional that we are looking at. Just give me a second. So let me tie the shoelace. And so let's recall what we have discussed. So if rho is rotating with the angular velocity omega, then what we know is that the string function involved with n minus omega over 2 squared constant on the boundary. So as I mentioned, this constant may be different from one connected component to another connected component, but here we are assuming that the patch is just simply connected. It's simply connected, so we don't have to consider that complicated case. We have only one connected boundary here. So all we need is this. And here the something that one can see is that. So I'm going to split this functional into two parts. So E1 minus omega 2 half. So this convolution part will be denoted by E1 of rho, and this second moment is denoted by rho. That this is a classical riddle by these. Also spell rearrangements inequality. So what it says is that if we have three functions, that looks similar to our first functional is always less than or equal to F star times V star convolved with H star, where F star, G star, or the symmetric decreasing rearrangements of F, G, H, respectively. So here, so what do we mean by this symmetric rearrangement? So instead of giving the rigorous definition, something it's the symmetric rearrangement is something like this. So just to make our life easier, let's consider the 1D case. So we have say x here, and then imagine you have a function that is not symmetric. So in 1D, let's suppose your function is not symmetric about any axis. Okay, and then we can rearrange each level set to make it symmetrized in such a way. So you look at each level set, say this one, and then there's the domain that corresponds to this level set, and then you put the same length here and do the same thing. Like if you pick this level set, not level set, this height, then you put this amount of portion like this, so that it's symmetrized by a certain axis. And then after this procedure, you're gonna get a symmetric function. So in 1D, you have this symmetric axis, just one axis, but in 2D or higher dimensional, then you're gonna get like radial functions. But then, what does it imply? What does it? What's the implication of this? Actually, there's one more thing that we need. So the equality, let me call this equation 1, say. Is achieved only if H are star. So what does it imply? So let's just ignore this part, because this part it's solely it's because of this rotating effect. But let's just focus on the stationary case. Then this this implies that this functional has a unique minimizer, and the minimizer has to be the radial symmetry function, right? So and that's the first observation. So we have some idea about the minimizer of this functional. And then what about this? The second moment. So its minimizer, like, it has to be also a disk centered at the origin, because like if your mass is away from the origin, then it gives you large values because its weight is x squared, right? So one can see that the second functional is also minimized when rho is radial. That's it. So we already have some intuitions about the minimizers of these two functionals. And then now let's consider the perturbations. To show that a rotating solution is actually a critical point to this functional. So given rotating solution, consider the continuity equation. For some given velocity vector v, and this equation takes the rotating solution as an initial data. So if we choose v, and then we run this continuity equation, and we assume one more condition, this v is divergence free. So as time goes on, like if you run this equation, then your patch, it changes the shape. And then we look at how this functional changes in time. Okay, so that's the variational argument. So all we need is just the divergence free condition for v. So we are going to show that for any v, this rotating solution is a critical point to that the function that we defined. More precisely, we make the following claim. We take time derivative we put the solution of this continuity equation into the functional, and then we look at how it changes in time, and then we evaluate this at the initial time. So that's the variation of this functional at the rotating solution. And then we are going to show that this is 0. That's the critical points. Okay, but how does it work? So let's do this. Let's just let me just copy the functional here. I'm going to write it as okay. No. Let's just take the time derivatives. Then we have so 1/2. So one time the time derivative hits the first one. We have rho t, rho, and but this is quadratic in rho, so the time derivative can hit the second one. In this case, we have rho and involved with rho t. And we have negative omega over 2 times x squared times rho and dx. We have the x. Right? the convolution is what is it called? Like self-adjoint? No, symmetric. So this, you can just move this convolution from this one to this one, so that this integral is just nothing but the integral of rho t and convolved in rho, so that this is just the same thing as the first term. So we only need to just multiply by 2 here. So we get rho t and convolved in rho. I'm going to write it as omega over 2 x squared, and then we can put them in one single integral, right? So what I did is we have the same thing twice, so I just canceled out this 1/2, and then I combine these two terms by like pulling out this rho t, because there's rho t here, and then put the two terms in one single integral. And then so rho t is just negative divergence of v rho times something. I'm gonna call it large C. We have large C here. Wait. Well, why do we have like two negatives? There should be one negative. And then you can do the divergence theorem, integration by parts. We consider the whole space. That is going to be E rho dot square C and then let me put this vector inner products just by rearranging them. Rho. This is just simple just very straightforward computations, and then we evaluate this at time 0. Which gives you at time 0, the rho is the characteristic function that is assumed to be rotating solution. But that is the just the characteristic function. So we just integrate this guy not in the whole space, but only on the domain of the patch. So our goal is to show that this term is 0, and then let's do one more integration by parts. But here, let's recall this condition for the solution to be rotating. So if the solution is rotating, then this guy is constant on the boundary, and that is what we are denoting by large B, right? We already know that this large B is a constant on the boundary. And remember, our domain is simply connected, so there's one connected component. So this is just single constant, and we don't really care about like a specific value because all we need is the gradient. So this quantity can be written as V times gradient of E minus C. So that this guy becomes completely 0 on the boundary, and this allows us to do another divergence theorem, integration by parts, and then we get negative. Okay. So on the boundary, we have V times the normal vector C the surface integral minus divergence of V, E minus C, dx, right? And then here what we know is that the phi is completely zero on the boundary. So this whole integral becomes zero. And I don't know if people can see what is here. So let me just. So what do we have? This at the corner is that so we were computing this quantity, and we were having this is integral v so I just copied what's in here to there because I'm not sure if you can see the blackboard because of the monitor. But we know that this phi is constant on the boundary, so this integral vanishes. And then another assumption that we are making here is that the V divergence free, so this one goes to zero, and actually we obtain this plane here. So we are good. Right? So let me summarize. On the one hand, we have that this guy. Oh, where is it? This guy. No. I'm going to just write it. This is idea better. So on the one hand, we have this the first variation vanishes at the rotating solution. Okay. And I erased, but the third step was to show that any critical point to this functional has to be a disk. So let's do that. We have like 15 minutes. So now we claim that if this guy is zero, in other words, this guy, which is equal to this one, so V times direct V. Right. On the one hand, we have this. And then the second point that I'm going to make is that if this quantity, V times direct V, is zero, then V is a disk. Okay. Of course, for omega in this region. But here we have that this first variation vanishes for any vector field V that is divergence free, right? So we didn't use any other conditions other than divergence of V is zero. So to show this, all we have to do is to find one single vector field V that is divergence free, and if that is 0, then it's a disk, right? So we are going to pick just one single equation. Technically speaking, I'm going to choose vector field V to be x plus grad T, where the gradient T is a solution to the following elliptic system. So function P is -2 in E, and P is 0 on the boundary. So there's some motivations. The first motivation is that, like, how can we, like, what kind of vector field V do we have to choose to make this argument? So the easiest one could be a gradient flow functional, because the gradient flow is the one in which the functional decreases the fastest way. So one can try, yeah, one can definitely try the gradient flow, and actually it works. But computation-wise, this vector field is easier. So that's one motivation, and another motivation is that for this gradient P. So so let's look at this X, the vector field. So if you have a patch, and then the vector field X is just radially stretching things in this way, right? Or one can think of X as a gradient flow of this second functional, E2. But this vector field is not certainly divergence free. When you compute the divergence of X, then it gives you 2. So we have to add something to make it divergence free. And this one is actually the one that is closest to X, like the closest divergence free vector field to X. So more precisely, V is X plus T satisfies W is always bigger than or less. W L2 is always bigger than or equal to the V minus X. So this V can be thought of as a projection into the space of divergence free vector fields. Okay. Or like we can imagine. So we picked the closest, the vector field that is closest to X, and then let's plug this vector field into this formula, which we already know equals to 0. Then we have instead of V, we have X plus T times gradient of T. So what was T? T was here. So I'm going to split T into the convolution part minus I just copied the definition of T here. And then let's distribute the things. So if X is multiplied to this one, then I'm going to just write it here, X times grad V involved with N, yes. And then x can hit this guy, but when we take the gradient, this is just negative of omega times x, right? So omega times x will give you negative x squared. And now we have the rest. P times gravity. So I didn't do anything complicated. I just did the distribution of the terms. And then I'm going to make some other claims. The first claim is that this guy, x times gradient x, whatever the shape of D is always equal to d squared over 4 pi. Doesn't really depend on the shape, but it only depends on the area of D, which we are assuming 1. And claim 2 is going to be is always bigger than or equal to d squared over 2 pi. This could be a little bit easier because we already know that this is minimized when D is a disk centered at the origin. So we only need to compute the exact value when D is the disk. And that is very explicit, and one can just compute, one can get this. And then claim 3 is going to be this term. P times gravity x is equal to negative 1 minus 2 omega times integral of p dx. And actually, there's one more claim. Integral p dx is always less than or equal to squared over 4 pi. And equality is achieved only if D is a disk. So I'm gonna postpone proving these 4 claims to the next lecture, but let's see how these 4 claims can give us the conclusion. Okay. It's very straightforward. So the first term is exactly equal to d squared over 4 pi. So we get d squared over 4 pi. Wait, here we have to make. So let's see, I'm sorry, let's see. So omega is less than 0 case first. Okay, so we are assuming that omega is, where did I erase? So omega is always living in like 0 and C. So there are 2 cases. The one case is omega is less than or equal to 0, or the second case is omega is bigger than or equal to 1/2. So let's see this case first. So in this case, omega is like non-positive number. So what we have here? Let me call it like equation 2. Okay, the first case, the equation 2 is equal to the first term is just d squared over 4 pi minus omega times something that is always bigger than this one, but we have negative omega. So this whole thing is positive. So we can replace this equality by inequality here, and then we have the d squared over 2 pi. So what I did is I replaced the second term by this inequality, and then we have the third term here that is equal to minus 1 minus 2 omega. Yes. So this 2 is always bigger than this one, and then that can be shown as like 1 minus 2 omega times d squared over 4 pi, which comes from these two terms. And then we have negative p, negative integral p. But this one is always greater than or equal to 0, right? That's what the fourth claim says. So the integral p is always lower than this one. So we get greater than equal to 0 because omega is a negative number. One positive, negative 2 omega is positive, so a positive number. So this equation 2, this guy is always non-negative number, but we can recall this part. So the equality is achieved when D is a disk. So the argument will be the following. So imagine, suppose your patch is a rotating solution, but that is not a disk. Then we are going to have a strict inequality here. There is going to be a strict inequality here. That gives you a contradiction because it says this is strictly positive, but we already have this is exactly 0. Okay. So omega less than or equal to 0 case can be done in this way. And then, how much time? I have 3 minutes. The second case will be omega is greater than or equal to omega. Then I shouldn't have erased. But whatever. wait, I erased. What did we have? So like, I'm sorry, I erased this the first variation that we just computed, but there was something 1 and minus omega x squared dx and d on d, and it was plus 1 minus 2 omega. Actually, it was negative. No. More precise. This is the one that I erased here, so there's nothing new. I just shouldn't have erased it. But let's just using these claims to compute this one this time. So as before, the first term is just exactly equal to the squared over 4 pi. And now omega is positive, right? So this one is always bigger than something. That means this one is always less than something. So we can replace this equality by inequality, and we plug in this. And then the last term is the claim 3 says that it's just equal to 1 minus 2 omega d squared, the integral p dx. What the third claim says, and then we also have the this greater p. No. Okay, so let me keep it from here. So that is still the same quantity as we saw. We have d squared over 4 pi minus integral PdS, right? So this is the same quantity as we saw exactly, but here we still have that this is always less than or equal to this one. So this one is always a positive number, but now the omega is bigger than 1/2. So this is a negative number, and so this one is always less than or equal to 0, right? This is always positive number that is multiplied by some negative number. And what can we see here? So again, we call that this equality is achieved only if there is a disk. So if we didn't have a disk, then we have a strict inequality. So that gives us a contradiction. Yes.
Yeah, when on basics are 1/2, couldn't it be that this is like identically 0?
If omega is exactly 1/2, then that is identical to 0. Yes. So actually, technically speaking, okay. So I'm gonna add this one. So this one is the same. So here, the equality is. Wait. Is this? Just let me think if the omega is equal to. Yeah. This one should be. So for this case, I didn't really mention because I didn't notice like if we really need. But in this case as well, the equality is achieved only if is a disk. So that in this case, so here instead of replacing this by this exact value, then you can just plug in 1/2. Then the argument will go through it the same way. So let me leave it details. And yes, I'm sorry for using 2 more minutes, but I think I can finish here. But I will prove these 4 claims tomorrow, and then not tomorrow, on Wednesday. Thank you very much. I think that's it.